Today, we're going to have a look at the electronic structure of the atom. Now, we know that if we look at an atom, we have the nucleus, and around the nucleus are these shells that contain our electrons. Now, our first shell can have a maximum of 2 electrons, our second one 8 electrons, our third one 18 electrons, and the fourth one 32 electrons. Now, as we move from the nucleus to the outside of the shells, my energy of each shell increases. Now, these shells are called my principal quantum shells, and we can denote them by N. So we have N equals 1, 2, 3, and 4. Now, the higher the shell number, the higher the energy of the shell would be. And the lower the principal quantum number, the closer the shell is to the nucleus. Now, inside each of our shells, we also get a subshell, and these are denoted by S, P, D, and F. Now, the energy of the electrons in the subshells also increase in the order of S, P, D, and F, with F having the most energy. Now, if we look at the principal quantum number 1, it will only have the subshell 1s. If we look at the principal quantum number 2, it will have 2s as well as 2p. The principal quantum number 3 will have 3s, 3p, and 3d. And then our principal number 4 will have 4s, 4p, 4d, and 4f. We can see here that 4s is below 3d, as well as 5s is below 4d. This is because 4s will have less energy than 3d, and 5s will have less energy than 4d, meaning that my energy increases as I move up the quantum shells. Now, it might seem very difficult to remember all these shells and subshells, but it's quite easy if we use our periodic table. So here in yellow would be my S subshell. Then in blue would be our P subshell. In pink will be our D subshell. And in green will be our F subshell. We'll go into more detail of how to use this method to work out the different subshells. So now we know that in each atom we have our shell. In each shell we have a subshell, but also in each subshell we have orbitals as well. Now our shells we know is 1, 2, 3, 4, and 5. We also know our subshells can be S, P, D, and F. And then our orbitals is the 3D configuration of the subshell. So this will be denoted things like X, Y, and Z. Now each orbital can hold a maximum of 2 electrons. Now we're going to focus on the S orbital and P orbital mainly. Now the S orbital has a shape of a circle, and in the S subshell there's only one S orbital. So if we draw the S orbital on a 3-dimensional plane where we have an x-axis, a y-axis, and a z-axis, it will look something like this. A circle in the middle, or a sphere. Now as I increase my shell number, the size of the orbital of S increases as well, so my sphere becomes larger. We then have our P orbital, and these orbitals are dumbbell shaped. Every shell has 3 p orbitals except for the first one. The p orbitals occupy the x, y, and the z axis and point at right angles to each other, so that they are orientated perpendicular to one another. So here we can see that the one dumbbell will lie flat on the x-axis, then another one on the y-axis kind of vertical, and then one in a 3-dimensional, so from front to back, on the z-axis as well. Now the lobes of the p orbital become larger and longer as we increase the shell number. So now we can conclude that, for example, the first shell will only have one subshell, which is called S, which means that it has a maximum of 2 electrons. If we look at the second shell, it will have 2 subshells, S and P. Now S can hold 2 electrons because there's only one orbital in it. But P can hold 6 electrons because there's 3 orbitals and each orbital can have 2 electrons. So in total, there's 8 electrons in the second shell. We then also get our d orbital. Now it has a maximum of 5 orbitals in the subshell, meaning that this subshell can hold a maximum of 10 electrons. Then we have our f orbital in our f subshell. Now our f subshell can hold a maximum of 7 orbitals, meaning that it will have a maximum of 14 electrons in this subshell. Okay, so let's summarize this to look at the bigger picture. So first we have our principal quantum number, or n, which is our shells. Here we have shell 1, 2, 3, and 4. Next we have our subshells. So shell 1 will only have subshell S, shell 2 will have S and P, shell 3 will have S, P, and D, and shell 4 will have S, P, D, and F. Then for each subshell there's an orbital. So the number of orbitals for subshell S is 1, P is 3, for D is 5, and for F is 7. So we can count these together to get the amount of orbitals per shell as well. So for shell 1, we only have 1 subshell and 1 orbital, so the orbitals per shell is 1. For shell 2, we have S and P. S has 1 subshell and P 3, so this is a total of 4, which means that for shell 3, there would be a total of 9 for S, P, and D. And for shell 4, there will be a total of 16 for S, P, D, and F. Now we also know that each orbital can hold 2 electrons. So for subshell S that only has 1 orbital, it will be a maximum of 2. For subshell P that has 3 orbitals, it will be 6. For subshell D that has 5 orbitals, it will be 10. And for subshell F that has 7 orbitals, it will be 14. So lastly, we can calculate the amount of electrons per shell. So the first shell will have 2 electrons, the second one 8, the third one 18, and the fourth one 32 electrons. So by using all of this data, we can compile an electronic configuration for each element. But before we do this, we need to understand how electrons behave. Now electrons spin around their own orbital. If they spin in a clockwise direction, we denote them as upwards. And if they spin in an anti-clockwise direction, we denote them as downwards. So when 2 electrons occupy the same orbital, they must have opposite spins and experience a form of repulsion known as spin pair repulsions. Therefore, electrons will occupy separate orbitals in the same subshell first, and with the same spin to minimize this repulsion. Now electrons will only pair when there are no more empty orbitals available within the subshell. So when this happens, they adopt opposite spins to reduce this repulsion. Now the way that I wrote it down here is called the electron box notation. Now each of these boxes, as I showed you, represents an atomic orbital. These boxes are arranged of increasing energy from the lowest to the highest. So let's look at an example, aluminium. Now aluminium has an electronic configuration of 1s2, 2s2, 2p6, 3s2, and 3p1. Now the 1 denotes the shell, the S, the subshell, and the 2's or the 6's or the 1's, those are our electrons. So we can write this in the electron box notation as well. So we'll first write down our shells with our subshells, and then we'll give little boxes for our orbitals. So we can see S has 1 orbital and P has 3 orbitals. So if we look at the 1s, we'll see that it has 2 electrons. We'll first draw the upward electron, and then if there's no other boxes, the downward electron. We'll do that for 2s as well, and then for 2p as well. So first, that needs to be a 6, sorry. So we'll insert one electron in each orbital, then the second electron in each orbital until we have 6. Then 3s is also 2 electrons, but look at 3p, it only has 1 electron, so we only write 1 arrow. Now this unpaired electron shows us that aluminium is a free radical. Now this means that an element has an unpaired electron. We can also represent this by drawing a tiny little dot next to the elemental symbol. So let's look at how we can use our periodic table to make this easier for us. So previously I did explain where the different subshells are located. So let's use oxygen as example. Here we have 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, and then oxygen would be 2p4. So we know that we end at 2p4. So if we had to write this on a line, we'll say it's 1s2, 2s2, and 2p4. Let's look at one more example. Nickel. So again, hydrogen is 1s1, then 1s2, then 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 4s1, 4s2, and here comes the confusing part, 3d1. So here we go down to 3 again, then 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, and 3d8 will be nickel. So if we write this out, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Now we can also use a shortened notation as well. And what we do here is we go to the previous noble gas, which would be argon. We'll put argon in block brackets and then just write the electronic configuration after that, which is 4s2 and 3d8. Lastly for today, we're going to look at ionization energy. Now the ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element to form 1 mole of ions. Now this is done under standard conditions, which are 298 Kelvin and 101 kilopascals. The units that we use for ionization energy are kilojoules per mole. Now these energies will always be positive because they are an endothermic process. This is because energy is required to break the force of attraction between the electron and the central positive nucleus. Now we're going to look at 2 ionization energies. We're going to look at the first ionization energy, which is the energy required to remove 1 mole of electrons from 1 mole of gaseous atom of an element. So for instance, calcium, when we remove 1 electron, it will become calcium plus an electron. Now the ionization energy for this is 590 kilojoules per mole. We're then also going to look at the second ionization energy. This is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous 1 plus ions of an element to form 1 mole of gaseous 2 plus ions. So for calcium, we'll have calcium plus, and when we remove an electron, we have calcium 2 plus an electron. Now the ionization energy for this reaction is 1145.4 kilojoules per mole. We can see that it's much larger. So let's try and see what the trends are in ionization energy. So firstly, as I move from left to right across my groups, my first ionization energy will increase. Now this trend is linked to the electronic configuration of our elements. There are 4 factors that affect ionization energy: our nuclear charge, the distance from our nucleus, the electron shielding, and the spin pair repulsion. Now, if we look at our nuclear charge, this refers to the number of protons. Now, we know that as our atomic number increases, so will the positive charge of the nucleus. So, for instance, sodium will have 11 protons and argon will have 18. Now, the higher the nuclear charge is, the stronger the electrostatic attraction between the nucleus and the outer electrons would be. Therefore, more energy is required to remove the electrons, so a higher ionization energy will be needed. Secondly, we have the distance from our nucleus. So this is our atomic radius. Now we know that as we go down the group, our atomic radius increases. This is because we add more shells. So hydrogen will have 1 shell, for instance, and francium will have 7 shells. Now, the greater the distance is, the easier it is to remove the electron because of the weaker attraction. So the ionization energy will decrease with increased distance from the nucleus. We also have electron shielding or inner shell repulsion that plays a role. Now, this means that electrons in the inner shells repel electrons in the outer shell and partially block the attraction of the nucleus. So the more electron shells there are, the greater the shielding and therefore the lower the ionization energy will be. Lastly, we have the spin pair repulsion. So we know that in orbitals that contain 2 electrons, the electrons experience a repulsion due to their charges. So this repulsion slightly reduces the energy needed to remove one of the electrons. So for example, if we look at oxygen and nitrogen, oxygen has 2 paired electrons, whereas nitrogen has 1 unpaired electron. Oxygen will have a lower first ionization energy than nitrogen. So overall, across the period, the first ionization energy will increase due to the higher nuclear charge and the same amount of shielding. But if we go down a group, the first ionization energy will decrease due to a greater atomic radius and more shielding taking place. Then, of course, we also need to remember about the unpaired and the paired electrons, and these give us some inconsistencies in our graphs. Let's have a look at the graph. So this graph shows us the first ionization energy for different elements on the periodic table as well as their atomic numbers. So we can see that as we go from hydrogen to helium, our ionization energy increases because we're going to go from group 1 to helium, which is a noble gas. So here, my atomic number increases, the amount of shielding stays the same, the distance or the radii from the nucleus to the outer electrons also stay the same. So my ionization energy will increase. But if I then go back to group 1 to lithium, it decreases significantly because suddenly I added another shell to my atom. This now means that the radii increased, the amount of shielding increased as well. We can also see a lot of inconsistencies, for instance between beryllium and boron. Beryllium and boron are both in the second period of the periodic table, but they're increasing from group 2 to group 3, which means that the ionization energy should technically be increasing, but it doesn't. Now, beryllium has a first ionization energy of 900 kilojoules per mole, and boron has less of 800 kilojoules per mole. Now, this is because the 5th electron in boron is in the 2p subshell, which is further away from the nucleus than the 2s subshell of beryllium. So, if it's further away, it will be easier to remove it from the atom. We can also see that there's a slight decrease in ionization energy between nitrogen and oxygen, and this is due to spin pair repulsion in the 2p orbital of oxygen. So if we look at the electron configuration of oxygen, in the 2p orbital, there's 2 unpaired electrons, whereas in nitrogen, there are 3 unpaired electrons. So nitrogen has more unpaired electrons, which means that nitrogen will have a higher ionization energy than oxygen. Oxygen still has 1 paired electron in its 2p orbital, which makes it easier to remove because of the repulsion. Now that was all about the first ionization energy, but we also know that we get successive ionization energies because usually there's more than 1 electron that can be removed from an atom. Now the successive ionization energies of an element will increase. This is because once the outer electron is removed, the atom becomes a positive ion, making a further electron being removed more difficult. So the more electrons are removed, the more the shielding will decrease, the proton to electron ratio will increase, and the attraction between the nucleus and the remaining electrons will increase. But as we can see in the graph, this increase is not constant. It all depends on the electronic configuration. So if we take calcium as an example, the first ionization energy for calcium is quite low. It's 590 kilojoules per mole. Second one is 1150 kilojoules per mole, then 4940, and so forth. Now if we look at the graph itself, we can see that there's 2 different jumps here. We have quite a lot of constants in between, but we have big jumps, and these big jumps show us the change of a shell. So here we have shell 1, shell 2, shell 3. Then we also have mini jumps like here, and this shows us the change of a subshell, but it's sometimes quite difficult to see. Now the first ionization energy is relatively low due to spin pair repulsion in the 4s orbital. So remember, spin pair repulsion, it repels each other, so it's easier to remove an electron. The second electron is harder to remove because this repulsion is no longer present, because now we removed one of the electrons, so the remaining electron in that orbital is alone and doesn't have the repulsion anymore. Then we have our third ionization energy, and this increases sharply as the electron is removed from the 3p subshell, which is closer to the nucleus. Now the fourth electron is also more difficult to remove due to the reduced spin pair repulsion within the 3p orbital. Now as we go on, these ionization energies increase because electrons are being removed from an increasingly positive ion. So we can use this data to predict or confirm electronic configurations. This type of graph identifies the number of outer shell electrons. It also indicates the group number by locating the position of a significant jump or ionization energy.